Today, we're going to tackle about geology and non-renewable mineral resources, earth and sciences, geology, and contemporary atrocities. And before we start, let me first quote this um, message from Will Durant. Civilization exists by geological consent, and it's subject to change without notice. Sure. We're going to tackle or answer some key questions and concepts. And these are the following. What are the Earth's major geological processes and hazards? How are the Earth's rocks recycled? What are the mineral resources and what are the environmental effects of using them? Then also we have how long will supplies of non-renewable mineral resources last? And lastly, how can we use mineral resources more sustainably? Question that we will be answering here is what are the Earth's major geological processes and hazards? And in order to answer that, first we need to know that the Earth is a dynamic planet. When you say dynamic, it undergoes constant changes, activities, or progress. Now, understanding the planet requires concepts in geology. And we all know that geology is the science that is devoted to the study of dynamic processes taking place on the Earth's surface and its interior. Now, the planet is dynamic as it is consists of three concentric zones. First, we have the core here. This is where the core, and then it is the inner core, and then it's here is the outer core. Then we also have the next concentric zone, the mantle. The mantle has an inner and outer part. And then we also have lastly the crust. To the definitions of the three concentric zones of the Earth or the Earth's cross section. So the first one is the core. So it is the innermost and extremely hot layer surrounded by liquid, molten, or semi-solid material. Now the core has two subparts, the inner core and the outer core. And then we also have the mantle. It's a thick layer coating the core. So it is the layer that covers the core. So it has an outer and inner mantle as well. Then this is where we can find the asthenosphere or the hot and melted rocks that can flow and can be deformed. And then lastly, the crust. It is the outermost and thinnest zone of the planet, and this is where life exists. Now, there are two types of crust. We have the continental crust and then the oceanic crust. Now, the continental crust constitutes 29% of the Earth's surface, I crust rather, and it includes the continental plate of the Australian plate, the Eurasian plate, the North American plate, and many more. And then we also have the oceanic crust, which constitutes 71% of the Earth's crust. So it includes the Pacific plate, the Indian plate, and those plates that are submerged underwater. Mentioned a while ago, Earth is dynamic, so it undergoes constant changes, constant activities, constant progress, or constant movement. So the Earth is moving. So if you look at this picture, the cause for that constant moving is due to convection cells. So convection cells is the directional movement, usually in circular direction of molten lavas or materials or rock materials due to the inner heat produced by the core. So here's an example of a convection cell. So it can contain several circular convection or directional movement of molten rock materials that led to the creation of tectonic plates. So tectonic plates are gigantic birds that constantly flourish and promote biotic life. So much of the geological processes of the surface occurred in between these boundaries or the boundaries between these um, plates, and maybe the cause of separation or divergent, collision or converging, and then or sliding with each other. So these forces creates the processes that we call mountain formation or volcanic formation or volcanic eruption, and then also earthquake. So if you look here, these are some of the major plates found on the Earth's crust. We have the North American plate, the Caribbean plate, the South American plate, or here in the Eurasian plate, the Philippine plate. Oh, we have our own plate, no, so Philippines, and then also the Pacific plate. So those red boundaries within each plate, it means that the plates of the Pacific and here the Scotia and the Nazca are diverging from each other, so they're moving away from each other. And then the one with boundaries with black and with ticks, they are convergent plates. So meaning they are moving in or colliding with each other or converging with each other. And then the ones with the plain line boundaries, so they are sliding with each other. So they're sliding with each other. It's either by north to south direction for each plate. When tectonic plates collide, this is usually what happens. So this here is the much denser or much heavier in weight oceanic plate. And then we have here the continental plate. So since um, oceanic plate is much heavier and then this one is much lighter, so the tendency is the continental plate would ride up over the oceanic plate and pushes it down into the mantle. So this oceanic plate will become the subducted plate due to the process of subduction. And this subducted plate would eventually melt into lava and resurface as magma when volcanoes erupts or there are volcanic eruptions that will happen. It moves apart of the opposite direction, magma will be released as largely driven by pressure. So the opposing direction of these two plates causes the rising of solid ductile hot mantle due to pressure. So as it rises, there will be opposing direction for this rising lava. And when it is releases into the ocean, in the surface in the ocean, it will become magma. And this magma that resurfaces the planet will create a ridge or a space in between these two plates. So an example to that here is the continental rift and the mid-ocean ridge. Now, what happens when oceanic plates collide with each other? So when they collide with each other, a trench would form at the boundary of these two plates as the denser is subducted into by the lesser one. So here, this one is the much denser, so it's the one that is being subducted by this another oceanic plate. So fun fact, the Marianas Trench, where we can find the deepest part of the Earth, is created by the collision of two oceanic plates. So one oceanic plate is subducted by another oceanic plate. And two continental plates collide, then the less dense plate is being pushed up by the much denser one, and it leads to the creation of mountain ranges or mountains. So if you look at this picture, so the much denser one pushes up this less denser plate, and it led to the creation of these mountain ranges. Now, there are two major geological processes that forms the planet. We have the first one, the internal geologic processes. These are usually caused by internal heat married with pressure and gradual tectonic movement that defines most of the surface features like mountains and volcanoes. So internal heat caused by the core, and then pressure, and then gradual tectonic movements or movements of plates like moving away or diverging away from each other or converging from it to each other or um, colliding with each other or moving together or moving sideways together. That's the first one. And then we have the external geologic processes, which are largely driven by solar energy and further influenced by gravity to wear down Earth's surface and move matter from one place to another. So an example here is weathering. So those are caused by climate or the wind movement, water movement, so or weathering. Mentioned a while ago as an example of external um, geologic processes. So we have here weathering. So these could be physical, chemical, and biological processes that break down rocks into smaller particles that help build soil. So we have physical weathering, chemical weathering, and biological weathering. Physical weathering, it involves wind, water, and temperature that breaks apart rocks without changing its chemical composition. So when a rock is weathered by water, it causes fractures. Or another one is when a plant root grows within that rock structure, such as this one in this picture. So it promotes cracking or breaking down of these rocks into smaller pieces. And then also thermal expansion. So when the temperature of a certain area rises and it grows hotter, so this creates individual grains of rock to be squeezed and released as finer stones. And we also have chemical weathering. So this is the decomposition of rocks due to chemical reactions between minerals in a rock and with the environment. So acidic compounds that interact with rocks would lead to the decomposition of rocks. So if you look at this picture, this one, when this rock is exposed to water and then acidic compounds, so chemical reaction happens and it causes this one, no, small holes occurring in the surface of the rocks, and then exposure to oxidation processes, and then water containing chemical compounds and degrades rock. So especially when there's acid rain, so rocks are exposed to these chemicals that would lead to the decomposition of rocks. Biological weathering, or a geologic process of fracturing a rock mainly induced by biological entities such as trees and other organisms. Now, roots from trees can also be a physical as well as a biological weathering, since roots are um, biolo- biological organisms. It's from a tree. So trees growth and roots that causes rocks, then lichens that produce chemicals that degrade rocks, and animals that bore for protection. Weathering is usually complemented by erosion. So what is erosion? So this happens when loosened and finer granules of rocks, mainly derived from weathering process, are transported from one part of the earth and deposited elsewhere. Now, erosion is driven by two driving forces. We have wind and water. So examples of water-driven erosion is kanima flowing streams, and then rainfall and surface runoff. And then blowing winds are those where finer granules of rocks are blown by the wind. So if you look at this picture here, so this one is driven by wind erosion. So it causes textural changes to the rocks or degradation or forming of patterns within the rocks. So those are examples no of um, wind erosion. And then this one is driven by um, water erosion. So it is created by kind of when um, ocean waves or sea waves um, collides with this side of the rock, and most of these loose and finer granular rocks are taken away by water. These are internally geologic process. So vents would eject magma from the Earth's interior. So vents from volcanoes. This is where usually the hot lava or molten lava will um, exit the interior part of the Earth. So volcanoes are equipped with a central vent, often called a fissure, that acts as exhaust for magma eruption. Then they are often formed, exist, and erupt along the boundaries between tectonic plates. So most of our volcanoes are found in boundaries between tectonic plates. So for example, the Asia Pacific Ring of Fire. So the Asia Pacific Ring of Fire can be found between the boundaries of the Pacific Plate and the Eurasian Plate, the Philippine Plate, the Indian Ocean Plate, or the Australian Plate, or even in the North American Plate. So the Asia Pacific Ring of Fire is where we usually mostly found most of volcanoes. Then magma that resurfaces the planet is called lava. And then released lava rocks, hot ash, liquid lava, gases that may be perilous and beneficial as well. Geologic process is an earthquake. So interior forces pushes tectonic boundaries, creating transform faults. So this movement in an existing fault may release tremendous accumulated energy in the form of vibrations called as seismic waves. And this is process is often called as earthquake. So it usually occurs along the boundaries of two tectonic plates. So when there's collision or diversion or moving away from each other or kind of scraping from each other or moving sideways from each other of these two tectonic plates, it creates movement and pressure that causes vibrations or the what we call the seismic waves. So it then forms earthquakes. The place where an earthquake begins, often far below the Earth's surface, is called the focus. So this is where usually the scraping or sliding with each other, collision or moving away from each other is focus. And meanwhile, the epicenter is the surface above this focus. So the energy release is in the form of seismic waves or seismic shocks, which moves upwards and outwards from the focus. So it creates a vibration, and the severity of an earthquake is measured by the magnitude or the measure of ground motion caused by the earthquake. So the primary effect of an earthquake is vertical and horizontal displacement of the ground with negative implications to the buildings, bridges, dams, and pipelines. So if we examine historical events, maybe the key to avoid um, earthquake-related casualties. So we can have better preparation. So we need to study historical events of earthquakes. Quakes in the ocean floor can cause huge waves that we call tsunamis. Now, tsunami is a series of large waves generated when part of the ocean floor rises or drops. Now, the main cause for these tsunamis is underwater earthquakes or where there is collision or scraping of oceanic plates below the ocean surface. So, the earthquake with release seismic waves, creating large upward motion of waves in the ocean surface. Now, how are the Earth's rock recycled? So, for us to be able to answer that question, we first need to know the composition of the Earth's crust. Now, the Earth's crust is composed of minerals. These are inorganic compounds that exist as crystalline solids. And an example to that is salt or sodium chloride. And then we also have rocks. It is a combination of one or more minerals. An example to that is granite. So it's a mixture of mica, feldspar, and quartz crystals. Three types of major rocks, and we'll start with the igneous rock. So igneous rocks are formed when magma wells up from the Earth's upper mantle and then cools down and hardens. So it forms the bulk of the Earth's surface, but they are covered eventually by sedimentary rocks. So the example of an igneous rock is a granite. So it is formed underground, and then lava rock is formed above ground. So most of igneous rocks are formed when volcanoes erupt. So the hot molten lava that is released by the volcano will cool down and then hardens to become igneous rocks. Rock is the sedimentary rocks. So they're derived from sediments, or it's a mixture of dead plants and animal remains and tiny particles of eroded rock. So they are formed because of um, weathering. So this collection of weathered sediments will be transported by water and wind and usually stored and deposited downstream or underwater sites. So as they accumulate and then coupled with weight and pressure, it converts this pile into a rock. So one example of that is dolomite and limestone. So these are compacted shells, skeletons, and other remains of dead aquatic organisms. It's a metamorphic rock. So they are formed when pre-existing rocks is subjected to high pressure, high temperature, chemically active fluids, or a combination. So changes in crystalline internal structure and physical properties and appearance are usually what we can observe with metamorphic rocks. And metamorphic rocks can be formed from sedimentary and igneous rocks. An example to that is the slate. So it is formed when shale and mudstone are heated. Then another one is marble, which is formed when limestone is exposed to heat and pressure. Are recycled very slowly. So the interaction of physical and chemical processes that change rocks from one type of another is called the rock cycle. So this geologic process is oftentimes takes over a million times, making it one of the slowest cycling processes on the planet. So how does an igneous rock is formed? So magma or molten rock as it rises to the surface from a volcano will cool down to create an igneous rock. So these igneous rocks are usually weathered away by wind or water or other biological processes and is eroded, transported, and deposited, and it will eventually aggregate or compacted to form sedimentary rocks. Now, igneous rocks can also be formed as metamorphic rock. So due to heat and pressure internally from the Earth's mantle or core, igneous rock will eventually form into metamorphic rocks due to the mixture of several minerals found on Earth. And then sedimentary rocks can be formed into metamorphic rocks as well due to heat, pressure, and stress. We use a variety of non-renewable mineral resources, meaning it cannot be replenished or it will take time to replenish. Now, mineral resource is a naturally occurring materials of the Earth's crust. So it may be in the form of non-metallic minerals such as aluminum and gold, or non-metallic minerals such as sand and limestone. Now, these minerals take so long to form, hence they are classified as non-renewable. So these are the following minerals that we extract for a variety of uses. We have aluminum for beverage cans, iron for steel production, gold for jewelry production, sand for construction, limestone to make concrete and cement, and phosphate salt as fertilizers. We utilize these mineral resources, it can also cause several environmental effects. So the extracting, the processing, and using non-renewable mineral and energy resources could lead to several environmental effects. For example, the mining, when we explore and extract ores of minerals like gold and silver, it can cause disturbance of the land, mining accidents, health hazard, mine waste, dumping, oil spills, and blowout noise and ugliness. And then during the processing of these minerals like gold and silver, um, transportation, purification, and manufacturing of such minerals will cause solid waste, radioactive material, air, water, and soil pollution, noise, safety and health hazards, ugliness, and heat. And then when during utilization, when we use the final product of the processed material, like in transportation or transmission to individual user or eventual use and discarding, it could lead to noise, ugliness, thermal water pollution, pollution of air, water, and soil, solid and radioactive waste, safety and health hazards, and then lastly, heat. Several ways to remove mineral deposits, one of which is surface mining. So in this type of removal, materials lying over a deposit are removed to expose and the resource for processing. Say, for example, the removal of vegetation lying above a deposit, or when we cut trees or remove the vegetation above that certain deposit. So these materials are stored as waste, generally called as spoils. And then these spoils from ore removal is left in the main mine area and generally called as mine tailings. Way of removing mineral deposits is the open pit mining. So large machines dig a very huge holes and extract metal ores as well as sand, gravel, and stone. And it usually leads to the removal of vegetation lying over the deposit. So here in this picture, you can see an example of open pit mining. So you usually use bulldozers to remove large sections of land from the Earth's surface. Of removal of mineral deposits is the area strip mining. So gigantic earth mover will utterly remove overburden, including vegetation. So a huge shovel will extract all the mineral deposits, and then the resulting trench will be covered again by the stored overburden. And the same process is usually conducted until the entire area is mined. Have here another type, which is the contour strip mining. So gigantic shovels and bulldozers, as you can see in this picture, cut series of terraces into the side of a hill. Then they will remove the overburden and followed by a power shovel to remove and extract the coal. Now, this highly erodible bank of soil called the high wall is produced after mining operation. So this high wall, it's very easily erodible. So that's one problem of this type of removing mineral deposits. The mountain top removal. So it utilizes explosives, earth movers, power shovels, and other huge machines to remove the top of the mountain and then expose seams of coal for extraction. So another one is the subsurface mining, where minerals are removed through tunnels and shafts. So it is employed when coals and metal ores are too deep to extract by surface mining. But one problem of this type of removing mineral deposits is if no proper engineering measures in the tunneling, um, it could lead to the collapse of a mountain if the area is on a mountain. Those mentioned methods of removing minerals has harmful environmental effects. So scarring and destruction of the land surface is one of those. So mining usually involves removal of forest vegetation, resulting into surface scarring owing to deforestation. And then it is very susceptible to weathering and erosion by water and wind, since there's no vegetative cover to protect the surface from it. Since there is no topsoil, nutrient and organic matter rich, regrowth of vegetation is slow, thus returning to its previous condition requires long process of primary ecological succession. Problem with over-extracting and overuse of non-renewable mineral resources is that it can be economically depleted. Now, the supply of non-renewable minerals can depend on two factors. first is that the actual and potential supply, and then the second one is the rate at which we use it. Now, we never completely run out of minerals, but it can be economically depleted when it costs more than it is to find, extract, transport, and process it again. So at this point, recycling and reusing, wasting less, using less, finding a substitute, or doing without it is a very necessary and urgent thing to do. So the depletion time necessitates proactive action. When you say proactive action, it's taking measures before an identified problem can happen or occur. But with the current way where we are using business as usual scenario model, um, it significantly shortens the availability of mineral resources. So if you look here in this graph, the red one represents the business as usual scenario where we only mine, use, threw away, or no new discoveries, and then there's combined rising prices in the utilization of mineral resources. So it only takes a short time before this for us to reach the depletion time, the 80% depletion time. Whereas for the improvement in technology brands such as green technology, like recycle, increase research by improved mining technology, higher prices, and new discoveries, now it will only delay the inevitable resource depletion. It's not a one-size-fits solution to the problem itself. But if we use sustainable practices that can significantly increase the depletion time, then it will take a lot more time before we reach the 80% depletion rate. So the better option here is the green one where we use, recycle, reuse, reduce consumption, increase reserves by improved mining technology, and then higher prices and new discoveries. Prices can also affect supplies of non-renewable resources. So if there's a competitive market where you can play with the supply and demand, then that could greatly affect the supply. So suppose when a resource is scarce, its prices will rise. So if you have your economics class, then that's what we call the law of supply and demand. Then this may encourage exploration for new substitute resources, better mining technology, and then make mining low grade or a profitable one. And then prices are kept artificially low owing to government subsidies, concealed as government funds, but truly taxpayers' money to prioritize economic growth and national security. Mining of lower grade ores, it can significantly increase the supply. But there's a disadvantage to that. One of which is the increased mining cost. And then the second one, it can increase the shortage of fresh water needed to mine. And then it can also have environmental impacts that are significantly higher than the previous other ways of extracting minerals. Get more minerals from the ocean. Now, there may be fragments of mineral concentration dissolved in seawater. So, definitely, there are large um, volumes or large concentrations of minerals that can be found underwater or underneath the surface of the ocean. But recovering it may cost significantly higher energy and money than they are worth. We are finding ways on how to solve this problem of resource depletion by finding substitutes for some scarce mineral resources. And one of those is the materials revolution, such as silicon, ceramics, and plastics are being used as substitute for metal. An example to that is the fiber optic glass cables that transmit pulses of light are replacing copper and aluminum wires in telephone cable. Another one, plastics, lightweight carbons used to create cars and aerospace vehicles. So these materials cost less to produce than metals and it don't need painting, therefore there is less pollution. However, it is not an universal panacea. No substitute for chromium in manufacturing stainless steel. Viable solution to mineral scarcity problem is sustainable use of natural resources. So these are the following steps that use no, we could use to solve this problem. Do not waste mineral resources. Then recycle and reuse 60 to 80% of our mineral resources. Include the harmful environmental cost of mining and processing minerals in the process prices of items. Reduce mining subsidies. Increase subsidies for recycling, reuse, and finding substitutes. Redesign manufacturing processes to use less mineral resources and to produce less pollution and waste. Then use mineral resource waste of one manufacturing processes as raw materials for other processes. And then lastly, we need to slow our population growth.